In this video, we're going to look at exponential functions. We're going to write and use exponential functions for a word problem. This video assumes you understand a little bit about multipliers and as well a little bit the general form of an exponential function. So if we see here in this word problem, it says the population of Qatar, maybe pronounced gutter as well, according to the World Factbook, is increasing at a rate of 4.94% every year. Suppose the population of Qatar is 1,699,435 people in 2010, and we'll assume that that 4.94% matches the data taken in the year 2010. So it says define variables and write an exponential function that reflects this scenario. Then the next part says use your function to determine the population of Qatar in 2014. And then use your calculator to estimate between what 2 years the population of Qatar will double. Okay? So, just briefly going to hit a little information about exponential function. Okay? Exponential functions all take the form y equals ab to the x. You could also say f at x for function notation equals this. A couple things you need to recognize with this standard form is that a is the initial value of what is being studied. B is considered to be the multiplier. Okay? And then y is the new value after change has occurred. And x is, in fact, the number of changes to the initial value. Okay? It's easy to get confused with that and think that, well, x is time or x is the year as we start doing these word problems. But you really want to try and keep in mind that it's the number of changes that take place to the initial value. Sometimes that number will be time. If something changes once a year and you study change 10 years down the road, then x would be 10 because after 10 years there were 10 changes. You're going to see in some problems that are a little more complex than the one I'm going to show you here that it's not so straightforward all the time if I said that the initial value changed once every 3 years. This is a situation where time would not be equal to the number of changes. So you want to make sure that you're making the generalization about x as such in an exponential function, that it's the number of changes. Okay? So let's take a look and see if we can extract the information that we need from this word problem and use this kind of standard form for exponential equations. This, I guess you could kind of look at this as like, this is the y equals mx plus b for exponential curves. When we think exponential curves, we think this equation. When we think lines, we think y equals mx plus b. So we'll get back here and define variables and write an exponential function that reflects this scenario. Okay? Well, I think the variables I'm going to deal with here are the following. I'm going to make the independent variable the year, and I'm going to call that t. Okay? And then I'm going to make the dependent variable equal to capital P, and I'll call that the population. Okay? Now, for us to be able to ascertain what A and B are, A is the initial value, right, which is pretty straightforward, 1,699,435. Sometimes when you're reading a word problem, it's just good to underline and put the letter A. And to find the multiplier, we realize this says increasing, so that means it's 100% plus the percentage they give you in the problem, which is going to give us 104.94%. But as a decimal, we will say that b equals 1.0494. That makes sense because when we multiply by that number, we get a small increase, and 4.94%, it's somewhat of a small increase in terms of percentage. Actually, in terms of population growth, it's quite significant Again, that happens because this is going to compound the population exponentially. Okay, so what does that leave me for my function here? I'm not going to really use y and x. Okay, if you notice, generally we talk about y and x, but in a specific word problem, I'm going to be using t and p. And just to review, you should know this, the independent variable kind of is your x, and the dependent variable is your y. So this will give me p at t equals 1,699,435 times 1.0494. Okay, let me just move this over a little bit. Okay, now the moment of truth for the exponent. To the, well, if I wrote t, that would not be correct. Okay, because if you notice the way I defined it, t is the year. Okay, but we need to also keep in mind, that the exponent has to be the number of changes. Well, that would preclude me from saying something like 2014 here, because if I put that there, in the year 2014, we've not had 2014 changes. That's just not correct. Okay? In the year 2014, we've had 4 changes. So what I need to do here is actually make my exponent reflect this phenomenon of it being equivalent to the number of changes. Write t minus 2010, which is the year the study was taken. Now, this should make sense because if I plugged in 2010 for t, the exponent would be 0, which means 0 changes upon my initial value have taken place. And in the year 2010, that is the case. You measured the population that year, it hasn't changed at all. So this exponent is a really legit expression for what we're trying to accomplish here in the problem. Once I say t is the years, you need to be able to plug in, t is the year, you need to be able to plug in a year to get the appropriate exponent. Now I could have defined this differently and said t is the years after the initial value was taken, which then just means in the year 2014, I would realize it's 4, and I wouldn't need that part, okay? But this is a little more elegant because it allows the user just to pop in the year and get the appropriate population. So that takes us to the next step where it says, use your function to determine the population of Qatar in 2014. Well, function notation here would mandate that I say it's P, the population, at 2014. So this is going to give me 1,699,435 times 1.0494 to the 2014 minus 2010. Okay? And again, what does this notation mean? It means to take 2014, plug it in for the input in P at T, and simplify. So from here I can go on my calculator, okay? And I'm going to determine this to the nearest person. So a little thing with your calculator real quickly. I'm going to hit the mode button and change it from float to 0 because I don't need to have decimal points in this problem because we don't need to be concerned with partial amounts of a body. Okay, so from here, I'm just going to enter this expression, which is 1,699,435 times 1.0494 to the, now just be careful, depending on your calculator, you have to do the exponent correctly. I have an older version of a graphing calculator, so I have to make sure I group the exponent together. So 2014 minus 2010. And if you notice, I put that in parentheses, so it would be all one number in the exponent. So this gives me roughly 2,060,956. Put in my commas for clarity, and it's people for the population. Okay? So I built the function, and then I used the function. Now I'm going to use this a little more differently in this next problem. If you notice, it says when will, use your calculator to estimate between what 2 years the population of Qatar will double. Okay, well, I'm going to bring my calculator back, okay, and I'm going to go to my y equals, and I'm going to enter the function 1699435, right, times 1.0494 to the, and then using my parentheses again, x, in this case, t, x will represent t, because it's the independent variable, it's the input, minus 2010. Okay? So, for there, if you notice, when I hit second table, okay, I'm looking for a very particular number. I'm looking for when the population doubles, okay? And it's starting me at 0, so we have to adjust that a little bit. So, let me come back here to where I can write a little bit, and keep in mind that I need to realize that the population started at A, so doubling it is 2A. So 2A is just going to be 2 times 1699435. So I want to know when the population is 3,398,870. Okay? So if you notice now, if I go back to my table, it's starting at 0, so that's not going to help me if x is the year. So let me go and hit second table set, and it would make sense for me to start in the year 2010 and go by ones, because now you realize that the study started at 2010. Okay, so that is hopefully going to help me zero in on this number that I need here of 3,398,870. Now, if you notice, it seems like all my answers in the y column are the same. It's because if you notice, I told the calculator not to round it off. Well, even in scientific notation, it's not rounding. I'm actually going to need it to round here, so I'll go back and put it in float. And then I notice here that I get more appropriate decimals. And I'm looking for a scientific notation here that is 3.4-ish times 10 to the 6. So I just need to scroll down and look for 3.4-ish times 10 to the 6, and it seems that that is going to happen between the year 2024 and the year 2025. So I can say between 2024 and 2025, the population will be around 3.4 million. Okay, so I hope that clears up a little bit about how to write and use an exponential function. I can't reiterate enough that you have to be able to work with this standard form of y equals ab to the x, understanding all its components. Initial value is pretty obvious in a problem. It's kind of where we're starting. It's a number that sticks out. The multiplier, you should kind of understand that they all start with 100% plus or minus, depending on if it's growth or decay. Y is the new value after x changes have occurred. And you have to be able to try and build a habit in your reading of understanding that x is the number of changes. Okay? Don't get hung up in thinking it's time all the time, because some of the problems get trickier, you'll get thrown off. But what'll counter that is if you just are strict and say x is the number of changes, you're going to be in better shape and be able to attack these problems more elegantly. So enjoy. Feel free to watch this again, and I hope it's helped.